My name is Airy Peralta. I'm a third-year graduate student at the University of Colorado Boulder's Ecology and Evolutionary Biology Department. During the last 2 years, I've been supported by the Indian Peaks Wilderness Alliance through their Patton Gellhorn Wilderness Research Grant to improve conservation tools in the Indian Peaks and the mountain ranges of Colorado.
I studied American pika, a cold-adapted small mammal which is the size of a russet potato with Mickey Mouse ears. Pika has a high metabolism and a thick double fur coat that prevents it from easily releasing body heat to the environment. Therefore, pika depends on summer's cold environments of its habitat to behaviorally thermoregulate. These characteristics make pika sensitive to temperature changes and make the species an excellent indicator for any temperature changes related to climate change.
Pika's characteristics have driven recent efforts to produce conservation models to assess whether and where pika might disappear and we might lose the ecosystem services the species provides. A recent distribution model for the species predicts that pika will go extinct within this century in Rocky Mountain National Park, a location only 16 kilometers from the Indian Peaks wilderness. However, like other models developed to predict pika occupancy at different locations within the United States, this model uses environmental data from climatic models built from weather station data. Weather station climatic variables, sampled at least 2 meters above ground and separated by several kilometers, does not represent the environment these small species experience. On the other hand, some scientists said that pika is showing resiliency to climate change. Resiliency is the ability of a system, individual, population, or landscape to quickly recover from disturbances like flooding, wildfire, or climate change effects. However, a system will only show resiliency until the maximum level of disturbance the organism can sustain is exceeded. In the context of American pika, this species might show resiliency to climate change by using the microclimates under the rocky slopes it inhabits. The microclimates under the rocks host colder temperatures than the exterior during the summer and hotter temperatures than the exterior during the winter. To understand whether these species will be affected by climate change, we must study the climatic dynamics that allow the talus to maintain colder temperatures during the summer and warmer temperatures during the winter. Whether these dynamics will be maintained as the planet warms up, and how hot do the temperatures inside the talus need to be for a pika not to be able to carry out its life history. Our preliminary results show that territories that are usually occupied have a warmer temperature during winter compared to those usually not occupied. Occupied sites are generally more stable during winter too. This means that the environment in those territories is better insulated, which agrees with the later onset of summer temperatures in those territories. This pattern tells us that snowpack cover lasts longer at those sites. Still, even though both occupied and unoccupied territories differ in quality, they remain warmer than the exterior. This data is a start on the task of describing the temperature range in which pika prefers to establish a territory and which might increase its chances of survival. Moreover, a climatic model is needed to simulate whether the preferred temperature range will persist if the exterior talus temperature rises up, as well as to predict those microtemperatures at places where we have not measured it directly, so that we can include this information in conservation tools. This summer 2022, we placed temperature sensors under the rocks and above the talus to assess how temperatures vary together. Besides free air temperatures, our current model uses solar radiation and topographic variables to predict summer microclimatic temperatures. We test the model using a dataset not included in the model training. We obtain that the model is fair at predicting the average trend in summer. Still, it fails to estimate the daily maximum and minimum. We might solve this error by including winter temperatures and the quality of the snowpack in the previous winter, as these variables aid in forming permafrost, the ice in the soil that cools down summer temperatures inside the tailors. Finally, another aspect we will consider is the diurnal wind pattern, which can help dissipate heat.